All right, folks, we are going to go over the next set of notes. So you guys are going to have all of your notes for this chapter done by the end of today. So grab your note packet. If you need the tiny packet of notes or the tiny notebook notes, just go up to the front of the room. I have them on that little table up next to my big lab table. So you'll see them. They're there. They're labeled for you. So grab your little notes or grab your packet, and here we go. We are going to talk about VESPR first, and then we're going to get into this thing called hybridization. So what we're looking at is VESPR is essentially the theory that explains why we have different shaped covalent bonds. So this is for covalent bonds, covalent molecules. And we know that covalent molecules, instead of just having a really set structure like ionic compounds where it goes every other positive, negative ion, and you guys have seen that before. I will remind you with a picture, maybe. Here we go. Where we are every other positive, negative, positive, negative, positive, negative. This is our very set structure for ionic compounds. All ionic compounds look like this. And then metallic compounds are always positive ions with their sea of electrons on the inside, right? My little dots in here are my electrons, and they're not in a set order. And this is just always true for these two. Now, covalent molecules, on the other hand, have very various, numerous different shapes. And so they come in all sorts of shapes and sizes, and you have seen some of these before from last year in chemistry. So hopefully some of these are familiar, but you're also going to see that there's way more shapes than we ever talked about last year. And that is because there's a ton of stuff, because we really simplified it for you last year. But we're going to look at all the shapes now. So the theory that tells us that we have these different shapes is called VESPR. It stands for valence shell electron pair repulsion. And what this is saying is it's going back to Coulomb's law, our favorite. And instead of what it tells us is, we've also often talked about Coulomb's law tells us that positive and negative attract. But Coulomb's law also tells us that if you're positive and positive or negative and negative, you're not going to attract. And that is what we're looking at here. We're specifically looking at repulsion between electrons, because electrons are negative. And so when we start to put our electrons around our atoms, we're going to see that they actually don't want to be near each other. Their bonds don't want to be near each other, right? So for example, here we have carbon, and carbon has a sulfur bonded over here and a sulfur bonded over here. And once we draw those bonds, I think sometimes you forget those are electrons, right? Those are little electrons in those bonds. And if I have electrons over here, they do not want to be anywhere near these electrons over here. Right? So they are going to go as far away from each other as possible, and that is why they go out on each side of the carbon, right? It's not, the sulfur is not coming up. There's not two sulfurs over here next to each other. They're going to go as far away from each other as they can because they're negative. They repel from one another. So this is the reason that we have all of these different shapes. And you can determine all of your different shapes based off of, I like to look at two different things. I like to look at the bonding groups right here, and I like to look at the lone pairs. And I'm always looking at the central atom. Okay, so we always base our shape, our 3D molecule shape, off of the central atom. Okay, so if I look back at this central atom, it's carbon, and I am going to ask myself, are there bonding groups? Not how many bonds are there, but how many things are bonded to it. So in this case, I know there are 4 bonds. That's great, but I actually want to know how many groups. So there's 1 sulfur attached and 2 sulfurs attached. So that's a total of 2 bonding groups, right? A sulfur and a sulfur. So 2 bonding groups. And how many, the next question is how many lone pairs are around this carbon? And this carbon has 0 lone pairs around it. So if those 2 things are true, this is going to be a linear molecule. And the distance between my 2 different bonds, I guess, are going to be 180 degrees. Okay, because they're going to be as far away from each other as possible, right? And that is a straight line, or 180 degrees, I guess. And so you're going to see that these bond angles are going to change throughout the different shapes. Also, the names are going to change. We look at the molecular geometry. It's the name of, or the shape of the molecule. We can also look at the electron geometry, but we're going to focus over here on this molecular geometry, so focus on that. And then again, I like to use these 2 to help me quickly figure out what I'm looking at here. So, just a couple other things that we have. I like to point out that there's two bents. So there's a bent here and a bent here. And that is because it's dependent on the lone pairs. So our first bent molecule here has one set of lone pairs, and this bent molecule has two sets of lone pairs. So both of them have the same name, but we see that the lone pairs are different. And when those lone pairs, when you have a second lone pair on there, it is going to take up space, and therefore your degree angle is going to change, right? So for this right here, I've got one set of lone pairs on the sulfur. So I've really got like an imaginary little electron sitting up there, and they're all kind of equally dispersed amongst each other. It's about 120 degrees. It actually looks a lot like this boron molecule right here, where they're all equally spaced around, right? And one of those spaces is just taken up by the electrons. Where that differs is down here, where we've got our sulfur, and our sulfur has two lone pairs around it. So these both need space up there. So that's actually going to push these bonds down closer to one another. This is going to be our 120. That says 120. This bond angle right here is going to be 109.5 about. So that is just because we need to make room for a whole nother set of electrons. And they don't want to be next to each other, right? They're not going to all sit on top of each other. So they need space. And then this shape is actually real similar to like our tetrahedral shape, right? Or our trigonoplanar pyramidal shape. They're all very similar. We're just taking off a bond and replacing it with lone pairs, right? So this has its one lone pair on the top, but everything is still about 109 degrees away from each other. And then our tetrahedral shape, instead of having any lone pairs, you're just putting that bond on there, right? And these are all going to be 109 degrees away from each other. So you'll find like there are some patterns amongst these, especially when there's the same amount of things around it. And you'll see that that's what this means over here. How many groups are around it? This has 1, 2, 3, 4 groups around it. This has 1, 2, 3, 4 groups around it. This also has 1, 2, 3, 4 groups around it. So they're all going to have really similar bond angles because they're surrounded by the same number of things. Okay, and that continues on. These are all probably the shapes you recognize. Once we get into the things where there's 5 things around the molecule and 6 things around the molecule, right, are these expanded octets that we've now talked about, we get some new shapes. So that's why you're going to start to see new shapes down here. And again, all follow that similar rule where if you have 6 bonds or 6 groups around you, right, 1, 2, 3, 4, 5, 6, that's our sulfur, or this bromine here, 1, 2, 3, 4, 5, it has lone pairs, 6, or the xenon, which has 2 lone pairs. So a group of 1, 2, 3, 4, 5, 6, all these 6s. Though their lone pairs are changing, they're all still about 90 degrees away from each other. And we'll pull out some molecules. You guys can actually build these and see what they look like in more 3D. But also, just so that you know, when you're looking at these, if you see the little dashed lines, that means it's pushing back, or it's like going back into the paper, right? So it's 3D backwards. And if you see these colored in full lines, this is a forward molecule. So that molecule would be coming out at you. Pushing back and coming forward. So this molecule is coming out at you. This molecule is getting pushed back. So that's what these are trying to show you that. And then they'll all be 90 degrees away. But again, I'll pull out some molecules. You can actually build these later on. As a reminder, we've talked about it, and just to refresh all of you on it, we always look at we look at 2 things, right, to figure out if it's polar. Are there lone pairs on the central atom? That will always make a molecule every single time. And there are some shapes that just always have lone pairs on the center, right? Any of them that don't have a 0 here in our lone pairs column, right? And that's a lot of them. Well, I'm not going to count them all, but all of these guys who don't have 0s in this lone pair column, those are all automatically going to be polar because they have those lone pairs on the central atom. And then the next thing is that if it's not symmetrical, and I do think all these examples are quite symmetrical, but maybe, for example, in this phosphorus pentachloride, if one of these chlorines was substituted with a fluorine, that would no longer make this a symmetrical model, and I'd have to go see what the bond is like, and maybe it would turn this into a polar molecule. So if it's not symmetrical, you can generally just say that it's going to be polar. So there you go. There you have it. Great. So that's my reminder on polarity. I'm going to stop this video, and then I'm going to start the next one. So first page done. There you go.